So really thanks for the kind introduction, Mr. Neugebauer. So you already told the title, so I don't want to repeat, but I would like to say in the beginning that I would like to introduce you these innovative lightweight glass-plastic-composite panels and how it could be a solution in the end for transparent lightweight glass structures or all glass systems. So first of all, you can see the build-up here on the right-hand side. So the panels are called NeroGlass, and they consist of an PMMA interlayer core, of a polymeric interlayer, and glass cover layers on top of the interlayer core, which leads in the end to a full transparency as well as a low self-weight compared to conventional panels. It allows for an edge treatment, especially the PMMA itself. So in the end, they actually look really similar to monolithic glass with the same edge treatment, and has really high optical qualities of the whole panels. The composite is actually manufactured in a chemical manufacturing process. This forms in the end the composite panels and leads to a really strong adhesion of the thin glass onto the interlayer core. The PMMA itself is relatively insensitive to environmental impacts. Therefore, within the scratch resistance of the glass on the surface, it leads to a really high durability. And all these properties what I introduced would lead to new transparent applications and have a high potential for these applications in all glass systems with a high transparency. I divided my talk into several parts. So first I would like to come up with the glass-plastic-composite panels, what I just introduced, and some application possibilities of it. Then I will go on to the development and the examination process within the research project. And then I will concentrate on the load-bearing behavior, which is actually the main part of today's talk. Afterwards, I will give a short introduction on an analytical calculation approach to exceed the results also on other build-ups. And finally, I will give a comparison to conventional glass systems, so monolithic glass, as well as laminated glass. Especially the creep behavior is here in focus. And then I will give a short summary as well as an outlook. So what are the application possibilities of these panels? Current products like all glass systems, so all glass doors or all glass partition walls, set high requirements for the transparency. They have to be lightweight, and they have to have an appealing design. Appealing design is currently performed or conventionally performed by eye-catching fittings, like you can see on the picture behind me. And these eye-catching fittings, this is our topic and the aim of the project, that we have the possibility within the PMMA interlayer core to form a direct connection into the PMMA. And this leads to smaller fittings, as well it allows due to the lower self-weight also for smaller fittings, and leads to maximum transparency of the panels, and for these applications, like said already, for all glass systems. There are also further possibilities like coloring the glass, and this also allows for further design aspects within the panels. However, these NeroGlass panels, as of yet, have not been investigated, especially regarding the requirements of the building industry. And this leads me now to the examination process and development process of these panels. So we have three main parts. So first of all, the composite and the composite behavior. So how do the panels behave over time? How do the panels behave in 4-point bending and other impacts on the panels? Furthermore, the interlayer material. So what is the interlayer material and how does it behave? So therefore, we are doing research into this material to form a material model in the end. And besides of this, the connection detail is under development. And therefore, we consider different types, so screwed, bonded, as well as inserted connections are considered with this development. The composite itself can be modified, especially the interlayer and the adhesion. And this is within the research project one of the focus to, in the end, fulfill the requirements of the building industry. And therefore, also durability tests are followed by, as well as artificial aging tests. And finally, of course, we want to have a structural solution, and therefore the connection detail as well as the maximum transparency is in focus. Today I would like to go more into detail on the composite itself, so the load-bearing behavior of the composite, to give a first assessment of the load-bearing behavior and compare it then to conventional glass. This was evaluated within 4-point bending tests in short as well as long-term test method. On the right-hand side, you can see the test setup and the dimension of a 4-point bending test according to EN 1288 part 3. While testing it and observing the deflections and using the Euler-Bernoulli beam theory and the deflection line, we can evaluate in the end the composite stiffness of the panels and derive a Young's modulus for the panels. And this allows in the end for a comparison to conventional glass. Also, the stress development was observed within the test methods to give in the end an evaluation of the stress behavior as well. Additionally, we performed long-term testings. So also here, the composite stiffness was evaluated over time. So the time-dependent creep behavior, especially of the interlayer core. And the creep modulus was derived here as well. And this was the assessment of the plastic creep behavior of the panels, which is actually also really important for conventional laminated glass with different interlayers. So let me introduce the specimens. So we had, for the short-term test specimens, 2 series, and we decided within the project to set 8 millimeters nominal thickness as a standard for our, or as reference. And we used either 2 millimeter annealed glass cover layers or 1 millimeter annealed glass cover layers. On the right-hand side, you can see that the 2 millimeter cover layers consisted of a green glass annealed, as well as the 1 millimeter cover layers as white glass. There are also other build-ups possible, so also thicker cores as well as other materials for the cover layers. And here we consider also chemically strengthened glass, because then we will achieve a high strength at a really, really low self-weight of the panels. Additionally, we tested long-term test specimens. Here we just tested 2 millimeter glass cover layers within the panels. However, further testings are going on with other structures and 1 millimeter cover layers, as well as I said, the chemically strengthened glass. To determine in the end the precise stiffness of the panels, the exact build-up was determined. So the build-up of the test specimen varied a little, and therefore we measured each layer by using a set of edge photos and a caliper. So this was really detailed and allows in the end for the evaluation of the composite stiffness in precise as well. So let's start with the short-term test method. So I already said with the 4-point bending, so we can see here again the test setup on the left-hand side as well as just schematic view on the right-hand side. We can see the load bearing as well as the introduction rollers and the dimension of the specimens with 1,100 millimeter times 360 millimeters in width. During the tests, we observed the deflections, so the vertical deflections at 3 points in the center as well as in the edge, and additionally displacement sensor under the load introduction roller on one side. Also, strain gauges measured the surface strain and compression and either tension in the center as well as one at the glass edge on the bottom side. And this allows in the end for the evaluation of stresses as well as the deflection. Regarding the test method, I have to say we deviated it a little regarding the standard. So normally the standard assesses the maximum strength of glass, but here we wanted to evaluate the load-bearing behavior. Therefore, we didn't test the specimens until full breakage. So the maximum force which was introduced was up to 400 Newton. We kept the load constant and released afterwards. And this allows in the end for the evaluation of the composite stiffness as well. So let me come over to the results here. So the results are depicted in a force deflection chart. Monolithic glass is shown as reference here, which is calculated for 8 millimeters. And we can see again the force of 400 millimeters as maximum value. The results were displayed or are displayed here in the chart for each specimen. So we can see a little scattering results within the lines also for the 1 millimeter glass cover layers, but this could be definitely returned to the scattering thickness, so the layer thicknesses within the panels, because this is really sensitive on the load-bearing behavior, especially on the maximum deflections then. The curving within the lines, so like we can see here that they were a little curved, they just occurred to the sensitivity of the test machinery. So in the end, we can say, when we have a look at the average here in dotted lines, that we have a nearly linear load-bearing behavior, compared to the monolithic glass on the left-hand side is also fully linear. At the same time, we can see now, or we can evaluate the Young's modulus. So maybe first again, for monolithic glass, we know it's 70,000. And with the 2 millimeter cover layers and the interlayer core of PMMA, we could reduce the rate out of 26% by still achieving a high structural performance, which is in the end a Young's modulus of 93% compared to conventional monolithic glass. For the cover layers with 1 millimeter, so the same thickness, the Young modulus was derived, of course, or obviously a little lower, with 63%, but we could achieve a rate reduction of nearly 40%. So that's quite high by still achieving a high structural performance. But how do the panels behave over time? So what is the creep behavior of the panels? Therefore, we did testing at room temperature. So here again, a modified test setup in the 4-point bending. Here, maybe you see it already, the dimensions were changed of the test specimens. So just half of the specimens were used with 180 millimeter in width. And this was due to that we could test more specimens at the same time. Furthermore, I have to say here, the load was introduced over a time period of 1,000 hours, room temperature, and the force was introduced by weight. So self-weight, or not self-weight, but weight was introduced, 110 newtons, and then kept constant over the whole time period of 1,000 hours. We observed the deflection over time with an inductive displacement sensor, as well as the stresses on the bottom center, so the maximum stresses at the panel on the lower surface. And this allows in the end for the evaluation of the creep modulus as well as the load-bearing behavior over time. And we wanted to assess the creep behavior of the PMMA interlayer core and also the composite behavior then. So not just the interlayer core, so so not just the interlayer core, so more the overall behavior of the composite. So let's jump over to the results here. They are depicted in a deflection over time chart. So we can see the deflection for monolithic glass here again as reference with around 4 millimeters under the load of 110 newtons. And then we can see each specimen from 1 to 8. And we also observed scattering results here for the deflection. And this was again due to the scattering thicknesses, so the layer thicknesses of the panels. And when we have a look at the average value, so it directly rises up until around 6 millimeters. But over time, we just have an additional creep deflection of 0.2 millimeter. And this is only 3% of the initial deflection, which actually, I can say that this is a really, really low creep behavior of these panels. And this is due to the high stiffness of the PMMA, even over time at room temperature. And therefore, we evaluated also the creep modulus. And even after a time of 1,000 hours, the creep modulus remained over 90% compared to monolithic glass. So this is quite high load-bearing performance at a several time period of 1,000 hours, compared to laminated glass, which is subjected to creep with a standard PVB and also some stiff PVB, but therefore I come later on. But how can the results now be extended to other build-ups as well as other geometries? Hence, we can use numerically methods as well as analytical methods. So FEM modeling is here one word I have to say. And I would like to introduce you just an analytical approach to compare it in the end to other build-ups as well as conventional glass structures. So here, the approach of elastic shear action. So we have a composite panel, so an elastic material behavior in the middle, and the cover layers of thin glass. And this load-bearing behavior actually lays in between the limits of monolithic limits, so full shear action, which would assess just one material, as well as no shear action. So that means the layered limit of the panels, so that each layer would deform separately and leads to an offset at the edges. But here, for the elastic shear action, we use a theory according to Wölfel, which actually allows to assess the stresses as well as deflections for composite and sandwich structures. And here we have to verify and have to check whether it is allowable or it is possible to simulate the load-bearing behavior of our panels. Therefore, a first assessment was performed and compared to the experimental results. So again, the average values of the experiments in the dotted line as well as the analytical in the dashed line. Again, I set monolithic glass as reference here. And within the short-term tests, we can see that there is a rough agreement with the analytical calculations. So we could not really get an agreement with the lines, but it allows still for a first assessment of the load-bearing behavior. And I have to say that we are with the calculations, or with the analytical calculations, on the safe side. So this leads to a first assessment to other build-ups and allows them to compare it in the end to conventional glass structures, especially laminated glass. Despite of this analytical approach, we also consider FE analysis, as well as other analytical calculation methods, especially for those composite panels, to allow in the end for a better agreement. Hence, we also have a look at the composite itself, so the material in the interlayer, and currently there's a material model under development, and this can be implemented then to the analytical or also numerical calculations in the end. As of next, I would like to compare these load-bearing behavior, what I observed, to conventional glass, like I already said. Hence, I checked the creep behavior of other panels. Here, I used monolithic glass again as reference, so the creep behavior over time, which is 0. So we always have the same deflections for monolithic glass. But compared to a laminated glass with a standard PVB or a stiff PVB, we can see that they are subjected to creep behavior. So for standard PVB, even after initial introduction of the load, we have a higher deflection compared to our panels, which are displayed with the green line, so the experimental results. And even stiff PVB develops a creep behavior, and after several time of around 100 hours, the deflections exceed the ones of the composite panels, of the normal ones. And here we used Prony series for standard PVB as well as the stiff PVB. Here it's actually Trosifol ES. And then we calculated these results. So in total, I have to say that our specimens or our novel panels have a really low subjection to creep, and even a stiff PVB subjects this creep and leads to higher deflections over time. And this, in the end, would allow for novel or new possibilities of the panels for structural applications. But let me summarize the main insights here. So I introduced you the panels itself. They showed a really high performance at low self-weight, and the load-bearing behavior was nearly linear. They are really not subjected to a creep at room temperature at the observed level of loading, and this reveals new application possibilities. To give a short outlook on upcoming research, we are currently checking the load-bearing behavior at different temperatures, so at lower temperatures as well as higher temperatures, also the creep behavior at higher temperatures. We are performing a material model for the interlayer core, for the PMMA, and besides of this, we also do the development of the connection detail. And Within the research project, we are currently checking if chemically strengthened glass can be an alternative or a way better alternative to get a high strength at really, really low self-weight. And all in all, I want to say that I gave you a first overview, I introduced the panels, and may it suits for some of your applications in future, especially with the high transparency as well as the novel connection detail. Last but not least, I want to say a big thanks to my project partners, so GPD Coatings in Germany, for the great cooperation and the provision of the test specimens. Also a thanks to the funders, and finally a really big thanks to you as the audience, and I would be happy to answer some of your questions now.
Thank you very much to keep the time.
Yeah, okay, perfect.
A bit more time for questions. Are there questions in the audience? Oh, over there.
So, thanks a lot for the presentation. Can you speak a little bit, or give few words about the interface between material? Is it glue? What is how you manage the interface between material, and especially the thermal different elongation between material?
So, like you said already, the adhesion, and this is performed in the manufacturing process directly. So it's not that we have a PMMA plate and then bonding the cover layers. This is one manufacturing process, which actually is secret manufacturing process of the GPD coatings. And the adhesion within these manufacturing is really good. So the adhesion of the cover layers is really good to the interlayer core, and this leads to the good load-bearing behavior. However, again, against the thermal expansion, because it's really different for the PMMA as well as the glass, we didn't have problems with this. We did climate change tests. Especially the company did them already in different ways. So also for the automotive applications, so which is a little higher exactly for the building requirements, and they fulfilled all these. So there were no crackings due to the difference in thermal expansion. But it's a really good question. Thanks for this.
Okay, thank you. Is there another question? No. Then, thank you once again for the presentation.
Hi there, did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!